We're going to introduce something called a linear combination. It is a way of combining vectors using only two operations, scalar multiplication and addition. Nothing else. No powers other than 1. The definition says if I have a set of vectors, u1, u2, all the way down to un, a linear combination of those vectors is some weighting of the first vector added to some weighting of the second vector, all the way down to some weighting of the last vector. All of these things C are called weights. They're just constants. Any constant you want. These things here in green are the vectors. All we are going to be doing is stretching vectors and then adding them up. We haven't even defined what it means to have a vector squared. As an example, this is a linear combination. 5 bunches of u1 minus the square root of 7 bunches of u2 plus 3 cubed bunches of u3. You said we can't use any other weird powers. How come you're using square roots and cubes? That's not a problem because all of those things are on the weights. The vectors themselves don't have any other powers other than 1. Now, the way that I like to think of a linear combination is that you can think of the vectors as your ingredients in a recipe. So if you're baking cookies, you need flour, you need eggs, you need sugar. So the vectors are those ingredients. The weights are the amounts. Now, depending on how much flour you put in, maybe 200 grams, or you need 5 eggs, depending on how much of each ingredient you get, you'll end up with a different cookie. And that's all a linear combination is. It says, tell me how much of each ingredient you want, and then put them together. Now, if I just want to bake a cookie, I'll tell you what ingredients, and I'll tell you how much of each, and then you'll go ahead and bake a cookie. You'll just add them all up, put it all together, and boom, there comes your cookie. But we want to go the other way. Can we determine if a given vector is a linear combination of some others? Now, as an example, can I write the vector b, which is 2, 1, as a linear combination of u, which is -2, 1, and v, which is, let's say, 1, 1? So in terms of the definition of linear combination, what I want to know is there some bunch of u and some bunch of v that I can put together to make them add up to b? Are there some c1, c2 that are going to make the left-hand side of this thing equal the right-hand side of this thing? Now, to try to answer that, take a look at what this really means. So I'm really curious as to whether or not I could write this. Now, if I use the definition of vector addition and vector scaling, then this is a linear system. When we have a linear system, we want to write this in augmented matrix form. It's much easier to work with. So we'll get 2, 1, 1, 1, 2, and 1. There's a wonderful shorthand. Now that we have vector notation, we can see that this is really just u and v as the columns of this matrix. And then I have the vector b on the other side. Within this one little example, we've got this vector linear combination form, we've got standard form, we've got augmented matrix form, which can be also written in this shorthand form. As you could probably guess, the answers to all of these things are going to be the same. So there's something in the textbook called proposition 2.1.7. The solutions to any of the above are the same. The easiest one for us to work with is the augmented matrix form, but conceptually the linear combination form is where we started. So what I'm going to do is row reduce this form. I'm just swapping the rows here. I'm now going to add twice row 1 to row 2. I'll get a 0, twice of that top row added to there, I'll get a 3, twice of that top row there, I'll get a 4. Keep row reducing again, 1, 1, 1, 0, 1, 4/3. And then I want to create a 0 above this pivot here, the second one. I'll add a negative bunch of row 2 and add it up to 1, and I'll put it as this form, 4/3 and -1/3. C1 is -1/3 and C2 is 4/3. The answer to my question is yes. B is going to be negative 1/3 bunch of U plus 4/3 bunches of V. And if you want to check for yourself, you say, okay, well, there's 1/3, negative 2 and 1, and 4/3, 1 and 1. You'll get 2 and 1. This is how the process works. We are going to be concerned with, can I write something as a linear combination? Is it possible for me to do it? And you're going to find that sometimes you will be able to do it like we did there, and sometimes you won't. So for example, if I now give you this set of vectors, negative 1, negative 2, and 2, 0, 5, and 5, and let's say W is 2, 0, 8, is B, this vector that I'm going to write down here, negative 5, 11, negative 7, a linear combination of these above vectors? Can I find some C1, and can I find some C2, and can I find some C3 that will add up to B? So I'm looking for these things. These are the unknowns. Tell me how much flour. Tell me how much sugar. Tell me how many eggs. I put this into augmented matrix form. I am going to form a matrix. So when it comes time to actually doing this and getting the numbers, I'll put it all in. And then it's just a matter of, once again, row reducing. We can add 2 bunches of row 1 to row 2, and that's going to give me a 0. The 5 will stay unaffected. 2 bunches of this is going to give me a 4. 2 bunches of that is going to give me negative 10. Added to 11 is 1. And sorry, negative 2 bunches up there. And if I were to do the same thing on the bottom, 0, 5, 4, 3, I can row reduce even further. And what I'm going to find is that I'll end up with a contradiction in the bottom. Because of this contradiction in the bottom row here, that means it's not possible to solve this system. And that means that no linear combination of these U, V, and W will make B. It's just not possible. Now, finally, I'll say, is 0 a linear combination of these 3 vectors? A1 is 1, 1, negative 3. A2 is 3, 4, negative 7. And A3 is negative 5, negative 8, and 9. So what I want to know is, can I write 0 equal to some bunch of A1 and some bunch of A2 and some bunch of A3? And remember, the C's are what I'm looking for. If I translate this, this is 1, 1, negative 3, 3, 4, negative 7, negative 5, negative 8, 9, and I want this to be 0, 0, 0. I'm going to want to row reduce this. Now I'm going to skip the steps. You can pause the video here for yourself and you can figure out what it's going to turn out to, but it will be the case that you end up with this. C1 is negative 4 C3, C2 is 3 C3, and this tells you that C3 is free. I only have 2 pivots. I am missing a pivot in this last column. And as soon as I have a missing pivot, I have a free variable. And so that means my solution, this solution vector, C1, C2, and C3, negative 4 C3, 3 C3, and C3. Or if I wanted, I could factor out this C3, negative 4, 3, and 1. How should I interpret this? I can choose C3, and then I'll get C1 and C2, and then I'll be able to form 0 from those 3 vectors. It's possible. As an example, I could pick C3 as 0, and that means that C1 and C2 will be 0, and then I'll get the duh combination. Yeah, none of A1 and none of A2 and none of A3 will in fact give me 0. This is kind of the silly combination. It's so silly, we're going to call it the trivial solution. You can always make that solution. If I pick something that's not 0 or non-trivial, then I'll get other solutions. Then I will be able to put together these vectors in what's called a non-trivial way to get an answer there. So this type of calculation is going to be our main focus from here on in.